Okay, it's 5 after. Let's get going. Anybody want to give an update on progress they had over the last week?
I didn't get that much done, but I was just trying something. I'm sorry, can I just share my screen here?
Yep, go for it.
Only take me a minute. Yeah, I was just trying something like that Alex had said last week. He said that for each of the species, they all seem to be within a sort of every single species, an individual species had like an F-min and F-max that was always the same. So yeah, like I just took a look at that. So you can see here, these are all the species. So each species in general just does have one F-min or F-max. So like this here's like looked at all of the examples within the data. So like some species have met, yeah, like there's a few that maybe have more than one, but in general most of them just have one. Yeah, so like species 10 here will always be between that F-max and this F-min. So what I was thinking of doing was, yeah, just cut down the spectrogram so it only goes between the min and the max. And yeah, like truncate all the images so they've just got like a slice in like this horizontal range, and then just have a classifier for each of the species. So it just restricts it down to that. But I haven't got that far yet because, yeah, I'd forgotten about the fact that like the scale here is log, so it's my mathematics isn't quite good enough to like let me just pull this bit out of the data yet. So I just need to work on that a bit more. But yeah, so what I was planning on doing was, yeah, for each of the species here, produce like just like an image that goes between these two frequency ranges, has it limited, and then yeah, have 23 classifiers, one for each of the species, and see can I sort of get anywhere with that. But I haven't got to try that yet. Yeah, so this is just like a notebook, whereas I sort of starting off to try and do it.
Oh, interesting.
Yeah, because like I know like other people have like tried just slicing it like vertically, but obviously for like species 17 here, all of this stuff up above and the stuff down below is irrelevant or whatever. So if I could just restrict it to like the range and find sort of what the interesting bit is within that range to detect the species, then I thought I could sort of progress that way.
Hi, Steve. Hi, Steve. Can you hear me?
I can, yeah.
Yeah, so just a comment about, so you said you want to translate the mel scale to frequency, right?
Yeah, so
because the plot here is in log scale, the mel scale, but you want to translate it into a frequency range. I think in the Librosa, there's a library called Librosa. There's the main library that you use for audio data analysis.
Yeah, so
I think there's a helper function to help you do that.
Is there? Yeah, because I wasn't sure. Yeah, so like I'm obviously when I'm drawing these pictures here, I was using Librosa to show the spectrogram.
Yeah, let me send you the link. Let me send you the link in the chat room, so you can check it out. I think this is the helper function you can use.
Okay, cool. Thanks. Yeah, because I've just got like a NumPy array here that I'm sticking into this.
You need to map the bin to the frequency, right?
Yeah.
I think that is the function you can use. Like, it's pretty handy.
Okay, cool. Yeah, so I was going to do that. Yeah, and like effectively just leave myself with these horizontal rows and chop them out. So I was hoping to like do that.
Question, Steve. How on a time from a frequency standpoint, you can you'd be just restricting or looking at that particular range. From a time standpoint, would you also, because the time duration for the species sound also varies, like the plots you're showing, correct?
Yeah, but so for each of these plots, all I want to do is like say, for like this one here, this is species 23. So all I want to do is say if species 23 occurs within this plot, and like when you're sort of giving the answers, you don't need to say at what time it occurred at, do you? You only need to say if species 23 was within the minute-long sound wave file. So I was gonna keep the whole, so I was gonna just keep the whole minute-long time period, but just limit the frequency. And just, as I say, have one classifier per species, and then sort of combine the 23 different classifiers. So like I would just...
would you though somehow also have to, and I'm thinking how it happens when you chunk and stuff too, rank order those classifiers within each recording? I guess it will happen naturally, right?
Yeah, so
it would happen naturally because the extent to which you would predict in the classifier would probably end up giving you a rank ordering anyway. But that would be interesting.
Yeah, so I thought I would have to stick like another network on top of it or whatever to sort of say whatever it is, the top 5 or to order them from the different classifiers.
Yeah, but you may not need to actually, now that I think about it, you may want to try it without, because anyways in your ranking you will get some scores, and as long as those, because all you care about is the ranking, not the value of the score. So as long as the values are in some kind of a range, you can just kind of combine them and see what ranking results without any effort to actually rank them.
Yeah.
You know what I'm saying? Like it will give you some probability, let's say, but then those probabilities, as long as you throw them into the same 23 list, ought to give you some ordering of rank naturally.
Yeah, so like that's sort of what I was hoping. So so I'm not sure. I'm not sure if anybody else that took part in the competition ever tried that or whatever, but yeah, as I say, it was all just from, like,
I think
Alex had shown like last week
trying
each species.
Yeah, trying all these is the good thing to do, right? I mean, I'm glad you.
I do saw some solution use that. Essentially, they bound the frequency per species and feed that crop image to the model. So essentially, you crop the frequency, also crop the time, feed it to model. It's actually, I think it's actually a good way to inform the model about the frequency range. But one tricky thing is you need to think about how you should do that in the inference time, because you don't have any bounding box in your test set. So you need to think about how you should work in test set.
So like in the test set, again, I would just sort of crop the frequency, but not crop the time. And so like each a test time, so I would still have like the 23 classifiers. I would just crop the frequency to generate the input for each of the classifiers. But yeah, like I wouldn't crop any of the time periods.
Yeah, I think I haven't tried that, but you can try. But by the time, just one question, like in in your mind, how would you, because different species has different size of bounding box, right? But by the time you feed it to the model, they should have the same, by the time you collate them into batch, they should have the same size. How do you align them?
Well, because you don't care where in the minute-long wave file or whatever, where the species occurred. You only want to sort of know if the species was there or not. So I don't think you need to align them. So like each model would just have a different size input vertically, but so
what I mean is that
because
if you feed, because the challenge is that like the model expect you to have a same image size. Otherwise, the model will have a unmatched, because how should I say? Because the matrix, because a model is essentially a bunch of weights, right? The weight that you use determines by the image size that you use. So it's good for you to think a way how to make them into the same size. Otherwise, it's the model cannot read them. Like
I was just going to have 23 different models.
Okay, I know what you mean. So 23 independent model for that.
Yeah.
Yeah, you can try. I don't know the result yet.
Yeah, so each one would just be a separate classifier, and it wouldn't be like linked to any of the others. It would just be to sort of classify if it thought that that particular species was present in the input data that was given to it.
I thought I talk about is only using one single model. Yeah, if 23 separate, then
yeah,
it's workable.
Yeah, so
yeah, actually, this approach is something that I would like to try after I try out the pseudo labeling. But the way I'm thinking about how it works is slightly different. So let me know if you get some result.
Yeah, sure.
I think this approach is promising.
I'll give it a go and see how far it gets me.
Yep, that'd be cool. Thanks, Steve. Yeah, you don't need to normalize or anything. You just feed the same frequency chunk across the 60-second test data to the same set of things, get an output for each recording, collate them, and then just score them.
Yep.
So, cool.
Oh, one more thing, like I forgot, like Steve, maybe you can combine true positive together with false positive if you are using this approach, because the true positive profile, because you have 24 models, right?
Yeah.
But you need positive sample and negative sample. If you only use true positive, you only get positive sample to train the model. So it would be good for you to have some negative sample. So for this, you need the false positive training set. I mean, there are two CSV, right? One is true positive, another is false positive.
Yeah, I hadn't actually thought about how I would use the false positive bit yet.
Okay. Anybody else? Alex, Yuri, want to share any?
Yeah. Let me know if you see the screen.
Yep.
Yep. We can see. I can see it.
Oh, just a FYI. Remember the weight and bias EDA2 I mentioned last session? So I just released that publicly. So I wrap it as a public kernel. So if you run this public kernel, you can reproduce that. And also I attach a link. So if you don't want to run anything and you want to use my EDA2 to inspect each entry, you can essentially just use mine. So here I I have saved around 1K of samples, evenly distributed by the species ID, and also distributed by the true positive and false positive. So you can do the group by and listen each of the species. You notice that the species has quite some distinguished characteristic. Yeah, you can try that out. I think I already attached the kernel link in the channel. So yeah. Apart from that, so as last session said, this week I mainly try out pseudo labeling. So the way I do that is, firstly, I try to do some EDA on the pseudo label. And then I try to collect those pseudo label as a CSV, combine it with the true positive CSV, and train the model again. So maybe we can look at the distribution of the pseudo label first. So I think this kind of graph, we already looked at that last session. What is new is the total number of pseudo label I mine at the end. So the way I do that is I set a threshold. I set the threshold to be 0.6, but I think it is something configurable. I may change it later on. If I set the threshold as 0.6, the pseudo label I can get end up to be 13K, which is a lot. Is almost 10 times. It's almost 8 to 9 times of the original true positive data set. Where by the time I try to inspect some sample, it quite makes sense actually. So I have some confidence there are some true label. So these are the distribution. So you can see some class is quite rare, like class 19, 22, 5, and 6. So I try to compare that with the true positive data set class distribution. So I think it's stored in another notebook. Let me see which notebook I store it. I think it's this one. So I think it's interesting to compare the class distribution that I get from pseudo label versus the class distribution we have in a ground truth data set. So essentially, if you so left-hand side is the distribution for pseudo label. Right-hand side blue bar is the ground truth distribution. So you can see they roughly align, but you can notice that for true positive, the class 5 and class 6 are not the minority, but you can see in the pseudo label is not the case. It's quite the minority.
I can't see a right-hand side.
Right? Oh, sorry. I only sharing a browser. Can you see that now?
I can see one browser window.
Can you see
I can
the
see
bar chart I'm sharing?
I can see the brown and blue bar chart. Yeah. So I can see one.
This is the one. This is the one. So if you look at the blue bar chart, it's the ground truth class distribution. So if you focus on class 5, it's not the minority, right? They have a roughly similar height with, compared with other class. But if you look at the distribution of class 5 at the pseudo label, you see it's quite a minority.
Yep.
So here I just highlight the difference. So what I essentially do is I try to plot out the distribution of the confidence score. Should I say it's a confidence score? It's a probability, right? Because each prediction is associated with a probability, right? So what I essentially do is for each class, I try to plot out their probability, to see how they distribute. Hopefully, each class should have a pretty dense distribution on the high end, somewhere like 0.9 or 0.8. But you can see it's roughly the case except some class. So if you see class 5 is not quite confident. So you see the mean is roughly at 0.7 to 0.8. It's also the case for class 9 and class 11. I think it's quite some interesting phenomenon. I originally thought like this kind of low confidence comes from the fact that they have low distribution, but it's not the case. If you look at class 5, it's true that it has a low probability and also have low occurrence. But if you look at class 11, is not a minority. So these are some observations about the pseudo label. So after this, I do a few rounds of training. Currently, the conclusion is that it does not improve. And it does not, it's getting worse actually. I'm not sure why. So right now I do 3 rounds of training. Firstly, I just naively include all the pseudo label. I don't do any weighting at first because it's easier to implement. Yeah, I think I'm referring to row 28. So you see the proper LB I got is just 0.74. Compared with the best I get 0.76, is pretty big difference. Yeah, even in the local seaweed, you can see there's a difference. So I'm talking about row 28 versus row 25. So by that time, I think about, so what I noticed about the training is that first it's pretty slow. It is 10 times slower. It is because of the fact that I have way more pseudo label than I have in the true positive. So one thing I need to work on is try to speed up the training loop, because it takes 10 minutes to complete one loop. So if I want to train for 30 epoch, which I usually do, it will take around 5 to 6 hours to complete one run, which is pretty slow and eat up a lot of my GPU limit in my Kaggle kernel. So definitely I need to speed it up. The bottlenecks mainly come from the fact that I do the MEL spectrogram transform on the fly. This is a bottleneck. By the time I time it, it takes roughly several seconds to do it, which is quite slow. I think it's also the main bottleneck of my GPU utility. Because by the time I notice my GPU utility, what I see is that the GPU utility is very low. So if I look at the percentage of the GPU utility power usage, yeah, I think it's the last graph. The utility rate is something like 20 something, which is very low. So I think if I can pre-compute the MEL spectrogram and save it in the disk, I can save a lot of computational power, so that I can speed up the data loading part, and as a result, boost up the GPU utility. So I would say that's the main bottleneck to my experiment, the speed that I do experiment. And also another thing I noticed is that the local CV is not quite correlated with the LB right now. I will talk about it later. So after this, what I essentially do is, because right now, for this configuration, I only train for 8 plus 16 epoch. So after that, I try to train longer and see whether it improves. So it turns out if I train longer, it gets worse. So it's a sign of overfit. So if I look at the graph, I see a serious trend of overfit, especially when I unfreeze the model and train. So this is one example. So you see, the blue curve is the training loss. Orange is the validation loss. The red is the validation LW metric. So you see that in the first 10 epoch, the training loss and the validation loss is pretty close. But at the 10 epoch onwards, you can see they start to diverge. The validation loss is increasing while the training loss is decreased. So this is the time when I unfreeze the model and train. So right now what I'm doing is that I don't do any unfreezing, but instead I only train the head and train it for 30 epoch. It's still in progress. I think right now it's in, is it complete yet? I think it's in progress. Oh, well, it doesn't seem it's improving. It's also, so you see there's also some sign of overfit. The LW rep is not great, 0.82. Compared with the best I can get is 0.88 is still some distance. So yeah, I don't think, I still believe the pseudo label should work. Should be a way to get me to 0.9 at least. It's just I need some calibration on that. For example, something I would do is I try to apply some penalty weight on the pseudo label, because for the label that is not that the model, for the label where the model is not sure, you probably want to apply higher weight, or higher penalty on that. So that's one thing. Another is apply a more restrictive filtering on the pseudo label that you get. Instead of applying a 0.6 as a threshold, I can higher that. That probably help, but if it still doesn't help, I think I need to inspect more on the model. I mean, there are several ways I can do, like, besides the two approaches that I just mentioned. Another thing I can do is that, because I will hypothesize that the model may be particularly weak on some classes, so I can firstly do some LW rep analysis per class to see what class that the model is particularly weak at. And then what I can do is I can exclude these class from the pseudo label. So to make sure the pseudo label is less noisy, Yeah, these are some methods. I think I'm still on the way to debug that.
One other thought I have is maybe use the false positives data somehow with, use that to influence your choice of pseudo labels, in the sense that, if it's detecting things where false positive says that's a false, I haven't thought through it, but completely to see how, but that might be another variant because it may be generating false positives. And if you have false positives, that you could potentially use that to screen out some of your pseudo labels.
Yeah, you don't want your model to learn from more false positive example. That will amplify the performance degradation. That
Right.
one, it's doable. It's doable. Like, I haven't thought about that. Like, actually, I can make use of the false positive to train a more, how should I say, a more reliable model. Yeah, there are a lot of approaches. Something like I can even do some ensembling by the time I do the prediction. So I train multiple models, and instead of using one single model to generate the pseudo label, I use an example of that. Seems like it's a way to reduce the variance. Yeah, so I think.
And by the way, what you saw, at least with respect to the head, and that's very interestingly, I've seen the same behavior too. I don't have the charts like you do, but I saw the same thing, that in a different variant that I don't have right now. When I try to train the base model, then it didn't help, and just freezing the base model and just training the head. And even there, I think one of the things before you joined, Alex, and training for larger epochs didn't make it better. It actually
Yeah, instead it's getting worse.
Yeah.
Yeah, but we say like compared, so I think this run is a run that give a pretty good result. I can see there's still some discrepancy between training loss and validation loss. You can see there's a roughly 0.03 difference. So this run is a run that I use pseudo label. So you can see there's, I think it's heavily, is it? Yeah, you can see it's also 0.03 to 0.04 difference. I would say the same, but you can see the trend is different. So you see, for this, they are converging, like their gap is the same, but for this, it starts to diverge. So that is fishy. I don't know why yet. So I think next week my focus will be keep sticking on pseudo label, but applying some more filtering or technique to clean, I would say to clean up the pseudo label I get, make sure it has higher quality. Also, I would like to speed up the training loop in the sense that I try to pre-compute the mail spectrogram. For the, I need more thought on that. Oh, I forgot to mention. I think this one I need more thought on that because if I pre-compute the mail spectrogram of the original audio, what I lost is that I give up the chance to apply augmentation on the audio space. So what I think is that I'm thinking a way to apply, because usually you apply the augmentation on the audio, right? You try to stretch the time domain, or you want to apply some Gaussian noise on the audio, something like that. But if you pre-compute the spectrogram, you can't do that. So I'm thinking whether I can apply this kind of equivalent augmentation on the spectrogram space. But for this, I can't find any resource in the Kaggle yet, but I think it's doable.
Yeah, no, actually, I don't know which specific augmentation you're looking for, but there were a bunch of ones that, the notebook I posted uses, and at least in a couple, and I might post a link to that too. So there was one notebook where, that I created, which utilizes both augmentation of raw audio and also applies augmentation after the spectrogram. Now, after the images have been generated. That didn't give me any incremental benefits, so I kind of abandoned it. And the audio augmentations, when used alone without augmenting the images, didn't give me any benefit either. So eventually I just stuck with using augmentation of the images. But I did try both, and I do know that some people on the competition have actually stuck with only using augmentation of raw audio, and some have done it in only the image space. So currently, at least, my results, the closest to 0.9 that I've gotten is augmentation with just the image, although I tried with both, and that didn't give me, it gave me slightly worse results. I wouldn't say it necessarily too far bad, but not any better, so I gave up on it.
I would say the augmentation that you do on the spectrogram space is quite different from the audio space, because the common technique I see that you will apply on the spectrogram is something like you try to mask out the time, or you try to mask out the frequency. But what I noticed is that they don't do the Gaussian noise augmentation or time stretching augmentation on the spectrogram. So I would say these.
Actually, there is a Gaussian. I believe, if I am talking from memory, I can when I post it. But there are Gaussian noise augmentations of the spectrogram that I'm using.
Oh, can you give me a pointer? Yeah, that would be great. Like, I am looking for that.
Yeah. It's from, it uses scikit-learn image augmentation in order to do that. Yeah, I'll post that notebook. And in fact, the notebook I already posted, I believe, has it. And one of the discussions, I forget which one, several weeks back, we kind of went to, I kind of went over in a little bit more detail because I was curious myself what these augmentations do. So one of the things I went over each one of the augmentations in the video space, and I distinctly remember there's a Gaussian one, there's some white noise one, and so there is noise addition or even stretching related ones. Of course, there's not a one-to-one relationship of what you can do, but there are similar ones. So yeah, I'll repost the notebook and you can take a look at it.
Yeah, I mainly look for time stretch and Gaussian noise. So if that works on spectrogram space, that would be great. That could help me save a lot of time, and at the same time, I don't lose any augmentation that I got in the raw audio. So apart from that, just some idea about augmentation. Because I'm thinking like, because in the training set, the sound, or the, how should I say, the sound that is mapped to the species is bounded by a bounding box, right? So what I'm thinking is that maybe I can extract this range and synthesize a lot of training data. So what I mean is that essentially I try to crop out this range, and then I randomly sample a audio subclip and superimpose this part onto the image. In this way, I can synthesize a lot of sample that is correspond to that species. There's just some thought about that. I haven't really formalized it yet, but I think it's a potential way I can synthesize numerous amounts of sample. So essentially, I just want to find out a way to disentangle the species sound from other sound. Yeah, and I think the bounding box could probably help. Yeah, I think that's what I want to share.
Cool.
So I posted a link to the chat. When you were talking about the confidence of your pseudo labels, I kind of got reminded that the technique that I saw yesterday, actually, when with neural networks that produce confidence that really is overconfident, that it's not really matches probability. There is a known technique to actually try to convert it into true probability.
Oh, okay.
I don't know if that will help at all in this case, but apparently it's very it's used in practice a lot. So
yeah, seems interesting.
You fit your you fit that parameter, a temperature parameter, into what you're like after you have your network and your specific problem.
So can I say this technique is a post-processing technique? I don't need to use it by the time I train the model.
Yeah, I think it's basically like once. Yeah, so like once you have your confidence, is to convert them to realistic probabilities. That's.
Yeah, it looks cool. Like, let me have a look. Thanks, Yuri.
Sure.
So, Atu, anything you'd like to share? I just saw you join.
Okay, no, I really haven't got anything so far. Sorry.
Okay, in which case, let me update a little bit of what I okay, let me see. So last week, Arto had suggested, right, that besides obviously the rank ordering which we looked at, it suggested with respect to mix-up, that mix-up itself is quite involved augmentation, therefore to drop the audio augmentation and just try it with mix-up, because my score with just mix-up was lower than what I was getting otherwise. So I think, and also that increasing the number of epochs by like 2 to 5 times. So I kind of tried that, and at least I would say the direction is positive, which confirms what Arto was telling us last week. Because if you look at my results, I kind of tripled the number of epochs. So this one is with 20 epochs. I dropped the other augmentation. So that's what the no aug says. And the high epochs is I did about 3x. So this 20, this 60 epochs obviously took a lot longer, but as you can see, my score did climb, although I didn't push it all the way to see whether it, if I did 100 epochs, whether it would get to my, forget the bagging score, that's not a fair comparison, but just a single, of course, I do the 5-fold averaging, but assuming that that's not, in a way that is, if you don't look at that as ensembling, then without any kind of bagging or combining or averaging models, it seems to get a better score, but still not up to 0.89, which is 0.893 was what was my single best score with 5-second with 5-second chops and predicting on 5 seconds, which I'll get to in a minute, why I say that. The other thing which we discussed last week was kind of trying a more complex head than and utilizing basic instead of just taking the output of the densenet directly, which is a 2048 flattened output directly to 24 values of the species, to introduce a FastAI equivalent kind of head, which takes it through multiple stages and also utilizes batch norm and dropout. So I tried that, but what I observed in the basic FastAI setup, and unfortunately I ran it before I noticed this, was the second layer dropout was very steep. It was almost like 0.8 or something, whereas the first layer was 0.4. So when I got this poor result, I said, okay, maybe I'm dropping too much in the last, I'm using dropout too heavily in the last layer, and my guess was correct, because if you see between this result and this result, the only change I made was reducing the dropout of the last layer from 0.8 to 0.4. And so that gave me a boost, and I forget now the additional change. I can go back and look that I made to get, but it's getting, with the past AI I had, it got close, but again, the best result I had was 0.893 as opposed to 0.890. The thing then that I also wanted to try, which, this was an interesting thought experiment that I did, which kind of produced some interesting results, and I haven't, I would say I have some very vague theories of what's going on, but it's I haven't completely concluded the explanation for my results. But here's what I did, and ignore these two, which are identical runs that I submitted by mistake. But here, what I was trying to do was utilize the 5-second training jobs that I'd done, but there's no reason per se that I could think of as to why, after taking a 5-second job for my in time intervals on my training, which gave me the best results, 5-second jobs, and then on inference also I was taking a 5-second job. But I started wondering whether that is necessary for me to do, meaning that why not use a 5-second job trained model on trying to predict a less than 5-second interval on inference. So I tried originally, and in fact, the reason for these is originally I tried with 2-second inference. So create a model with 5-second jobs in time and train the model that way, and then use that model to predict on a 2-second time job. And so for a 60-second interval, a 2-second time job would mean 30 slices. But I found out that simply ran out of memory on Kaggle. So I wasn't able to, as Alex was saying, I might need to kind of then store the jobs and blah, 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 which I wasn't, I just wanted to try the idea. So I backed off the 2 seconds, and instead I was trying with a 4 seconds. And it's kind of interesting that when I do an inference on a 4-second job, but with a model trained on 5 seconds, it actually gave me poorer results than if the time job exactly matched, right? Because I'm obviously getting 893 when I use a 5-second trained model on a 5-second job inference. The 4-second inference did work, because in that case, the increase in the number of slices is only from 12 to 15. For a 5-second job, the number of slices I have is 12, and for a 4-second job on the inference, it's 15. So that's not too big of a increase in my slices for inference. So that worked as far as memory limitations were concerned, but obviously my results weren't that great. And then interestingly, I tried the same thing with kind of the same concept, trained 10-second model, meaning a model trained on a 10-second chop of time, and then I try to predict on a 5-second chopped inference, and you can see that worked horribly, meaning it really dropped my scores. So that obviously says, you know, and this is where I was saying I was kind of thinking up all the reasons why why we would see that drop, because obviously you are training on a much larger time window and trying to predict on a much smaller time scale, and that simply doesn't work. The 5 to 4, I guess the time scale delta is not as significant, so it continues to perform not too poorly. Then the interesting thing I thought of is, because I saw a significant improvement from when I went from 10 seconds chops to 5-second chops, and because the memory still worked for 4-second inference, I was wondering whether if I created 4-second chops for my training, whether that would work better than my 5-second chops. But you see that was somewhat counterintuitive results. My 4-second chop training model gave me poorer results than my 5-second chop training models. Again, don't quite know how to explain this result. Why, when I'm training with 4-second window as opposed to a 5-second window, it actually drops by some, whereas when I go from 10-second window to a 5-second window on my training, it actually improves by quite a bit. So those were things that I was trying to play with. Again, you know, obviously with ensembling and bagging and other things, I can get to close to 0.9 or maybe even just across that line, but I was still trying to get if you will, a single. That's why I hesitate to say single model, because I'm still doing 5-fold things. But assuming you ignore that for a minute, at least a single structure that would get me to around 0.9. But I think I've exhausted all my different at least approaches within this context. So next week, I think I'm going to kind of try entirely new approaches to see like anything in the contrastive learning space and or something different to see whether I can get past the 0.90 barrier, but with still hopefully a single structure or a single model rather than an ensemble of models. Because ensembling and bagging, especially with the rank-based approach, we saw already last week that it did give me good results. So once I have that kind of capability, then I can combine it with even my current 5-second job to boost the model scores even further.
I can't remember. Last week you'd said how long the longest sort of time period is for a species. I can't remember how long that was. Like, what would be the longest amount of time that one species would?
Somewhere I said, yeah, you're right. I thought I saw somewhere that it was within 10 seconds.
Right. Yeah, like I was wondering, is it?
The longest is 7 seconds. It's a class 23. Most of them are less than 4 seconds. Class 17 is lasts for 5 seconds. So if you set the 5 seconds as a interval, so you won't sacrifice much species except class 23. But if you set to 4 seconds, you will cut out additionally 3 more class.
Yeah, like if I was wondering if that was what was causing the difference, where your 4 seconds is truncating some species, and your 10 seconds is a bit too long, it's adding more noise in. So that's maybe why 5 works best.
That explains it. Yeah. that explains kind of what I'm seeing with 10, 5 versus 4, because 4 is too narrow, 10 is probably all inclusive, but doesn't get as good a result when you start going to inference, and 5 is just kind of in the sweet spot. So that makes a lot of sense.
Perhaps if Alex is saying like the longest species is 7 seconds, perhaps you could try 7 seconds.
Yeah, that's a good point too. The only problem why I stuck to 4, 5, and 10 is they're even divisors of 16.
Oh yeah, yeah. Go for 6.
I think there's a trade-off here. I think like 7 could fit all the species, but there's a trade-off here because I noticed there are some species that only last for something like 1 second. So if you set the period to be something like 7 seconds, you may make the model less targeted on those species that is pretty short. You know what I mean?
Yeah.
I'm not sure.
Yeah. No, in fact, this prediction here shows that, right? Like when I use a 10-second window, but then I try to do an inference on half the time, I mean, look at how the score was.
And also, by the time I hear the audio, I will notice that in some occasion, I'm not sure whether it's frequent or not, the species will call together. So you have multiple species calling together. So if you set the period to be longer, there's a chance that there will be a higher chance multiple species occur at the same time.
Yep, good point. Excellent point. Yeah, I mean, I forgot about it, but yes, I do remember seeing that yeah, if it's 10 seconds, the chances of your having multiple species, and especially my training, because I'm training with cross entropy, is not multi-label but single, so I'm only picking up the most significant one in that, and which means I'm losing what you're saying. So yeah.
So that's why I see some top solution, they do a minor tweak on the loss function. So what they do is something like a mask, how should I say, a mask binary cross entropy loss. So what they do is, because right now we have one class for each example, but we use binary cross entropy, right? So we treat each class independently. So what they do is they will mask out. So let's say in one example, you have class 20. So by the time you feed in the loss function, you will mask out all the class. You will mask out all the other class and only leave out the class 20. So in this case, you will inform the model about the presence of class 20, but you won't inform the model about the absence of other class, because possibly other class may present. So they will do the same on the false positive. So you just inform the model a particular class is absent, but you won't tell the model other class are present or not. So that's what I mean by masking. You know what I mean?
Yeah, I kind of saw that, or at least, I knew some, but I was waiting till we tried different approaches and then look at kind of some of the best results to see what we are missing in terms of approaches. Yeah, but I'm vaguely aware of what you're mentioning or the goal of it. I haven't yet figured out how to do it.
Yeah, for the masking probably
and I didn't want to check
the next thing I would like to try, because I think it's a pretty easy tweak. Like what you essentially do, just is to mask out the loss of other class. Just focus on one single class.
Yeah.
So I have a question regarding this fact that like spectrograms basically are different from images in a way that say the same pattern in high frequencies basically might correspond to different entity than like basically the same pattern in low frequencies, right? And I wonder if anyone saw some kind of how do you incorporate this knowledge into your architecture or your training?
I think it's something to do with normalization. Because by the time we use ResNet, because ResNet mainly trained on some normal image, but the fact that we are using a Mel spectrogram, which is quite an extraordinary image from the standpoint of ResNet. So I used to think whether we should apply some special normalization by the time before I apply the ImageNet statistic. I mean the mean and standard deviation, because you know if the Mel spectrogram look quite differently from a normal image, you can expect that statistically the distribution is quite different. So I'm thinking whether I should apply some special normalization beforehand. So I saw that some people try to do a sample-wise normalization, essentially just a min-max normalization per sample. Also, some people try to apply a global mean and global standard deviation. I tried out the sample-wise min-max approach, but I would say it's not quite different. So which means that if I don't do any min-max normalization and just apply the ImageNet mean and standard deviation normalization, the result is quite similar. That's what I found so far.
Yeah, that's also interesting. And I saw this. There is a paper called Audio Spectrogram Transformer, and they compared starting from they trained it on audio set data set. It's quite big, but yeah, quite big by audio standards, but not if you compare it to ImageNet, I guess. So they trained from scratch on this audio set and started from ImageNet pre-trained this DIT transformer and VIT transformers. So, and there was a note about this patching, so how you construct patches. And you can basically, in this vision transformers, they construct patches by dividing image into 16 by 16, like yes, by this patches 16 by 16. And the authors of the paper observed that if you train from scratch, you get better results if you construct patches of shape 128 by 2. So taking this high vertical stripes. And so that was what was bothering me even before, that the spectrogram, it's not quite equivariant translationally in height, right? So only in this time along time axis, but not along frequency axis. And but the convolutional networks we use, those are like translational equivariant in both frequency and time axis. And I wonder if there are some kind of modifications that like take into account this specifics of spectrograms, or maybe that's not important at all. So just that.
No, to your point, Arto, I've seen discussion of size of the image. I mean, in fact, I think I shared what I tried myself too, right? And there are 2 points, kind of 2 independent points, I think, that you're making. One is the, the fact that spectrograms or there isn't, unlike in images where the bottom line shapes at different locations are identical here, if they happen at different vertical locations, they are not equivalent, right? Because they are happening at different frequency ranges, if they're happening at different vertical things in the spectrogram. That's one. And then the whole convolution being whatever, equivariant or invariant to the vertical and horizontal dimensions. And I saw, and we discussed kind of the size of the spectrogram thing that you brought up also, right? So when you say 128 by 2, do you mean 128 on the y-axis, and then when you say 2, meaning 256 on the x?
So that's basically in transformers, what they do, they take this patch and just unroll it into a vector and then feed it to transformer together with some patch embeddings, like page positional embeddings. So that's just 128 by 2 like pixels, I guess. And yeah, that might depend on how you like hyperparameters of your spectrogram, right? But I think they just tried to keep the numbers close to or the same as with 16 by 16 patches, the number of pixels, but just a different slicing style.
Because after our discussion, I think I mentioned it, but I tried different, remember in the base notebook I borrowed from and stuff, the size of the image was chopped to, and I'm talking from memory, but it's like 256 by 200 or 400 or something, by 400 I thought. And then I tried varying the height and increasing the width, and that actually, I mean, as I believe you had predicted and stuff, and we had discussed, the sensitivity on height is what matters, right? And there's no reason, and in fact, as you increase the x-axis, you're just basically, if you're actually sampling equivalently from correctly from SR and including the time sample, then it's one thing, but otherwise you're just stretching through interpolation and stuff. Same thing for the y-axis beyond 128. So that did not help. And there are several posts discussing, in this competition at least, as people played with it, they seem to arrive at some, and I forget what the numbers exactly are, but some numbers for the height and the width of the spectrogram that would give you results. But obviously, it also depends on what sampling rate you're using to generate the pixels corresponding to, and the MEL frequency you're choosing. But since most, and the blog post you had posted also pointed to, I think, 128 mels. Almost everybody so far that I've seen is sticking with 128 mels, which means that spectrogram far beyond that on the y-axis is not very useful, because you're basically duplicating or stretching the pixels in that case.
So what you mean is you try resize the spectrogram, but you found it didn't help.
Yeah, so the base notebook that I had borrowed from was resizing the image to, I can look it up, but it's like, I think 256 by 400. So if you take a 128 mel spectrogram, convert, blah, 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 and the image, or even when you're producing the, kind of taking the raw audio and generating, you can just resize the image. That's what the notebook was doing. And I tried running it without any resizing of the image, resizing it differently, and seeing whether the size of your spectrogram image that you generate in pixels, right? The pixel image height and width, whether that has any impact on, because some of the, as I was telling you, I applied augmentation primarily to the spectrogram. Although I tried it on the raw audio, I didn't use that eventually. So my best results are just with augmenting the image. So I tried with different image sizes, and that didn't seem, in fact, in some cases it got worse. And that tallies with the observation that as long as you use 128 mels, going beyond that number necessarily on the y-axis doesn't really buy you anything. So, for example, let me see which one. Let's see whether I can. See what I'm talking about. Here, you can see that the I just resized to 224 by 400, and I tried it with different variations of that.
Oh, if I don't do any resizing, does it better?
I saw. I'm trying to recall. Now I need to go back. Let me look. See, again, it's a function. I did try. Slight in my case. I say my case because it was slightly worse.
Okay.
Right? The NRS, this is no resize. Right? And this is 256 by 400. Right?
Quite big a difference.
Got me very close, right? Yeah. And then my best results was with what I showed you, which I believe is, what is it? 224 by 400. Right? Whereas I tried, this? Yeah. So I tried no resize, 256 by 400, and my original was 224 by 400. And that gave me the 224 by 400 is my best result so far.
I see. Maybe I should also try resize. So by the time you resize, do you proportionally resize along x-axis and y-axis? or you don't, or you only stretch one axis?
No. Yeah, that's what I was thinking, but no. It seems fairly arbitrary. That's why I was saying, see, the 200 is not that far off from 128. So technically, I think that's what Atto was mentioning, and I believe that if this number is just 128, I think that should be good enough, but it's like, slightly more. But when I take it to 256, which is 2 times 128, it got slightly worse. So this 400, I don't quite get how he arrived at it, but it just uses it. But obviously, if you extend it too much, then again, I ran out of memory because you can get into trouble. So it needs to be, and that's where I saw some discussion on the discussion forums that this being close to a square seems to help, although in this case, it's more of a
It's about
1:2 rectangle.
It's about the aspect ratio.
Yeah, but that's something I played with as well to get an understanding of what seems to matter. And what seems to matter is the X can't be very large, but the X doesn't really change things too much. But I think the Y, that's where if you're using 128 mils, then if you go too far up in this, then, actually I misspoke. When I try to increase the number of the size in the Y dimension, because what I was trying to do was let me spend a lot of pixels on describing the mels, right? Because the mels is in the Y axis. So I said, let's make this 512 by 400, and it wouldn't even, it ran out of memory in compiling those images or creating those images. So I had to stay down to less than, the max I could go here was 256, I think, or slightly higher, but think of that as kind of the limit. And then this one was much larger when I didn't restrict the size and I did the no resize at all. So I just commented out this line and ran the rest of it.
I see.
And then obviously, as I told you, I got the best result with this, but I got very close to it with 256 by 400 as well.
Yeah, probably I would try resizing as well. It's the simplest trick I can try.
Yeah.
My hypothesis is that
you can see
the aspect ratio may matter because in the
right, and also
in the series space, you usually when the image is kind of stretched. So what we usually do is you won't stretch it into square, but instead you will pad it with some blank pixel.
Yeah, and then while we're at it, Alex, here are the SK image transforms and filters, and there's like Gaussian, and you can add random noise, which I believe is here is the random Gaussian.
Wait, you add the random, how do you add this?
And
so you treat the image,
kind of,
wait. So you do a pixel-wise noise injection? Wait, let me see.
Yeah, I forget now of, it's been a while since we looked at what the specific
because it doesn't make sense
do.
to me, like, because adding a Gaussian noise on audio space is different from adding a noise in the pixel space, because like it is, if you add the noise in the audio space, it is unlikely the noise will map to a high frequency range. But if you add the noise in the pixel space, it's equal likely to have a noise on the high frequency range compared with having a noise in the low frequency range. But I just wonder whether they will make a difference. What I mean is that
I didn't.
The noise should not be uniform.
if you are talking about adding a noise to audio space.
Yeah, so that's why I said I don't know that these augmentations in the image space are equivalent to what you would want to do in to the raw audio. Again, I saw in some notebook that there were only, of the many things, a couple of only a couple of augmentations in the audio space seem to matter. So I did try augmenting using, I believe there's an just like albumentation, there is something else that you can use for audio augmentation or something like that. And I used that to try a notebook with, so for example, let me see. Yeah, here, this notebook, I tried just the audio augmentations. Forget that. Yeah, this audio Mentations is a library that allows you to do audio augmentations. And so these were the things that I used from that. The pitch shift, clipping, distortion, and then, this is just composing the two. So now these are in the video or image space, and the ones I pointed to are in the audio space. So this particular notebook, if I did both, I did the augmentation in to the raw audio and then applied the augmentation to the image as well. That didn't give me as good results. Then I tried only augmenting in the audio space with no augmentation in the images. That didn't give me better results. And then I went back to just using the augmentations I had on the image space. So you can see here, my best results were this. I tried just in the audio augmentation. So I dropped what I was doing with respect to image augmentation, and I used only audio. That dropped and again, I didn't try more than what those two augmentations I showed you. Maybe if you use different augmentations or different combination, but then, that's where I'm not, I haven't spent a lot of time figuring out which augmentations in audio would work best and why. But it dropped it somewhat. So I tried combining both in the augmenting the raw audio and the images. That got it slightly better, but it was still worse than my best results. So I dropped the audio augmentation completely and just stuck to image augmentation. But, I can't claim that these experiments are conclusive. It's just empirical, and you could probably do more by understanding what the raw audio augmentations are doing and combining them. I didn't play beyond what I saw and the narrow set that I've used.
Yeah, I'm looking at the audio mentation repository. I noticed most of the augmentation is applied on the audio space. Wait, let me see. Such as the Gaussian one.
Yeah, audio augmentation is for augmenting raw audio.
Yeah.
The Psi image one is the one that applies augmentation to the spectrogram images.
It seems like there's not much toolkit available for spectrogram space augmentation. Yeah.
Actually, the scikit image thing gave quite a number. I mean, this was just 3. There's a whole lot more available here. From here, SK image, transform, filters, color. There's a whole bunch in SK image.
But those are the
Exposure,
augmentation you
utilities,
usually
can go there.
do. But are they usually the augmentation that you apply on ordinary image?
Yes, I believe. Okay, great. Over to Stephen and analysis results. Hopefully some progress. Anybody else to share any comments? If not, thanks everybody for joining and share, and we'll meet again next week.
Sounds bye.
Thanks.
Okay.
Thank you.
See you later. Bye.
Thank you. Bye.
Bye, guys.